Hello everyone. So, today we will solve few problems on natural convection flows. Although we will discuss about turbulent flows in forced convection in detail in week 11, but today we will just show few correlations for turbulent natural convection flows. So, generally if Rayleigh number is greater than 10 to the power 9, then natural convection flows is to be said as turbulent flows. Whatever heat transfer relations we have derived in last 3 lectures, so those are valid for laminar flows where Rayleigh number is less than 10 to the power 9. Later Bajan proposed that Rayleigh number is not the criteria for determining whether it is turbulent or laminar flows, it is the Grashof number. So, if Grashof number is greater than 10 to the power 9, then it is turbulent natural convection flows, and few correlations we will also write based on the experiments. Turbulent natural convection over a vertical flat plate, for this critical Rayleigh number earlier it was proposed as based on your characteristic length was of the order of 10 to the power 9, but later Bajan proposed no, it is the Grashof number, okay, which actually determines, this is the critical Grashof number which determines whether it is laminar or turbulent flow. So, it is equal to 10 to the power 9. So, as you know that Rayleigh number is the product of Grashof number and Prandtl number. So, critical Rayleigh number you can say that it is 10 to the power 9 into Prandtl number. So, depending on Prandtl number, so Rayleigh number will vary. So, this is the critical Rayleigh number. Okay. So, it will determine whether flow is laminar or turbulent. If Rayleigh number x is greater than 10 to the power 9 into Prandtl number, then the flow is turbulent. So, obviously, it is natural convection flow. So, Churchill and Chu in 1975 they proposed one correlation for turbulent flows, and let us write that correlation first. So, Churchill and Chu relations in 1975. Okay. So, they proposed for uniform wall temperature condition. Okay. Average Nusselt number is equal to 0.825 plus 0.387 Rayleigh number based on the height of the plate to the power 1 by 6 divided by 1 plus 0.492 divided by Prandtl number to the power 9 by 16 to the power 8 by 27 to the power 2. Okay. So, this is for turbulent flows and this is derived based on the experimental value. So, this is known as correlation. So, Churchill and Chu correlation. Okay. And for uniform wall heat flux boundary condition, okay. So, this 0.492 you can replace with 0.437. So, this is the same relation except the value of this for 0.492. So, it will be 0.825 plus 0.387 Rayleigh number to the power 1 by 6 divided by 1 plus 0.437, okay, in case of uniform wall heat flux condition, divided by Prandtl number to the power 9 by 16 to the power 8 by 27 to the power 2, okay. And this relation is valid for 10 to the power minus 1 less than RAH less than 10 to the power 12. So, you can see this is also valid for Rayleigh number less than 10 to the power 9. So, it will give reasonably good results, and you can see in case of uniform wall heat flux condition, this Rayleigh number will be based on your height of the plate and the temperature difference, that will be average temperature difference, because for uniform wall heat flux condition you know that temperature will vary along the plate. So, obviously it will be based on H and your Tw minus T infinity. So, this wall temperature you have to consider as average wall temperature, okay. So, then it will be average temperature difference, based on that this Rayleigh number is defined, okay. Even for laminar flow, Grashof number less than 10 to the power 9, Churchill and Chu proposed another relation. So, for laminar flow, where Grashof number is less than 10 to the power 9, another correlation was proposed by Churchill and Chu. In 1975, okay, and it is valid for both uniform surface temperature and uniform wall heat flux. And uniform wall heat flux conditions. So, that is given as average Nusselt number 0.68 plus 0.67 Rayleigh number to the power 1 by 4, 1 plus 0.492 divided by Prandtl number to the power 9 by 16 to the power 4 by 9. And Eckert and Jackson also performed the integral analysis for turbulent natural convection flows, and they proposed these Nusselt number relations. So, let us write that. So, using integral relation or using integral analysis, for turbulent natural convection, okay, Eckert and Jackson proposed. So, Eckert and Jackson derived the local Nusselt number as 0.0295, Prandtl number to the power 7, 1 plus 0.494, Prandtl number to the power 2 by 3 to the power 6 to the power 1 by 5, Grashof number to the power 2 by 5. So, this is local Nusselt number, and average Nusselt number based on the height of the plate, it is 0.834 Nusselt number, okay, local Nusselt number at y is equal to h. Sorry, this is based on y, because generally we have written in terms of y. Okay. So, this also you can write y because height of the plate, okay, along that direction we have taken y. So, this will be y. So, while solving the problem, first you have to determine the Rayleigh number, and depending on the Rayleigh number you have to see whether it is laminar flow or turbulent natural convection flows. Then you have to use suitable formula to calculate the average heat transfer coefficient or the heat transfer coefficient. Okay. So, first let us solve this problem. A 0.3 meter long glass plate is hung vertically in the air at 27 degree centigrade, while its temperature is maintained at 77 degree centigrade. Calculate the boundary layer thickness at the trailing edge of the plate and the average heat transfer coefficient. If a similar plate is placed in a wind tunnel and air is blown over it at a velocity of 4 meter per second, estimate the boundary layer thickness at its trailing edge and the average heat transfer coefficient. So, you can see first using natural convection you have to find the boundary layer thickness and the heat transfer coefficient, and later case if it is a forced convection flow, then you have to calculate the boundary layer thickness and the heat transfer coefficient. So, in this case first you have to know the properties. So, generally properties are calculated at the film temperature, that means average temperature, and thermal expansion coefficient beta we calculate as 1 by Tf, where Tf is the film temperature, and this film temperature you have to write in Kelvin. Okay. So, these properties, sorry, this is air at Tf. Okay. So, it is 27 plus 77 divided by 2, so 52 degree centigrade. So, 325 Kelvin. So, beta you can calculate 1 by Tf as this, and the thermal conductivity, the kinematic viscosity and Prandtl number are given. So, first you find what is the Grashof number. So, Grashof number you can calculate as G beta Tw minus T infinity into L cube divided by nu square. Okay. So, you can see you can calculate 9.81, beta is 3.07 into 10 to the power minus 3, temperature difference you can write 77 minus 27, then you have the L. So, you can write this based on H. Okay. So, height of the plate you can see 0.3 meter. So, it will be 0.3 cube divided by nu square. So, 18.41 into 10 to the power minus 6 square. So, you will get it as 1.2 into 10 to the power 8. Okay. So, you can see obviously Grashof number is less than 10 to the power 9. So, the flow will be laminar. Okay. And once you know Grashof number, you can calculate the Rayleigh number. So, it will be product of Grashof number into Prandtl number. So, it is 1.2 into 10 to the power 8 and Prandtl number is given as 0.7. So, it will be 8.4 into 10 to the power 7. Okay. So, using integral solution, we have derived the boundary layer thickness delta by x, and also we have found what is the Nusselt number, and from there you can calculate the heat transfer coefficient. So, we will use those relations here. So, from integral solution we have found, okay, delta by y, this we have found 3.93, 20 by 21 plus Prandtl number to the power 1 by 4, Rayleigh number into Prandtl number to the power minus 1 by 4. So, in this case at the trailing edge you have to calculate the boundary layer thickness. So, we will write y is equal to h. Okay. So, you can write delta at y is equal to h. So, it will be first you write h is your 0.3 meter. So, 0.3 into 3.93 into 20 by 21, Prandtl number is 0.7 to the power 1 by 4, Rayleigh number 8.4 into 10 to the power 7, Prandtl number 0.7 to the power minus 1 by 4. Okay. So, this you can write 0.3 into 3.93. So, this if you evaluate you will get 1.134, and this if you evaluate you will get 1.142 into 10 to the power minus 2. So, finally, you will get 0.0153 meter. So, if you write in terms of millimeter, then so 15.3 millimeter. Now, you can write the average heat transfer coefficient. So, first let us write the expression for average Nusselt number, and from there we will calculate the heat transfer coefficient. So, you know the relation from the integral solution as Nusselt number is equal to 4 by 3 into 0.508 into 20 by 21 plus Prandtl number to the power minus 1 by 4 and Rayleigh number into Prandtl number to the power 1 by 4. Okay. So, if you put these values, so 4 by 3 into 0.508. Okay. So, this if you evaluate you will get 20 by 21 plus 0.7 into to the power minus 1 by 4 and 8.4 into 10 to the power 7 into 0.7 to the power 1 by 4. So, if you evaluate these values you will get finally as 51.86. So, now you can write h by k as 51.86. So, average heat transfer coefficient you can write as into k. So, k you know 28.15 into 10 to the power minus 3 divided by 0.3. So, you will get h bar as 4.866 watt per meter square Kelvin. Now, you have to consider the forced convection, and first you calculate the Reynolds number, then check whether it is laminar or turbulent flows. You know that if Reynolds number is less than 10 to the power 5, then flow will be laminar for flow over flat plate case, and then you use the suitable relation. So, for forced convection, Reynolds number will be u infinity h by nu. So, it will be 4 meter per second 0.3 divided by 18.41 into 10 to the power minus 6. So, you will get 6.51 into 10 to the power 4. So, the flow is laminar. Okay. And if you remember from the Blasius solution, we calculated delta as 5 h by root RE h, right. So, you will be able to calculate 5 into 0.3 divided by 6.51 into 10 to the power 4 to the power half. So, this you will get as 5.88 into 10 to the power minus 3 meter. So, it will be 5.88 millimeter. Okay. So, you can see in case of forced convection flow, your boundary layer thickness is much smaller than the natural convection boundary layer thickness. So, now calculate the Nusselt number. Okay. So, average Nusselt number you know it is 0.664 RE h to the power half Prandtl number to the power 1 by 3. So, you can see you can write 0.664, this is your 6.51 into 10 to the power 4 to the power half, and Prandtl number is 0.7 into to the power 1 by 3. So, if you calculate this, you will get 150.4 and H bar will be 150.4 into K. So, thermal conductivity is 28.15 into 10 to the power minus 3 and H is 0.3. So, you will get as 14.11 watt per meter square Kelvin. So, you can see here that in forced convection flow, obviously your heat transfer is higher than the natural convection flow. Now, let us consider the next problem. A metal plate 0.609 meter in height forms the vertical wall of an oven and is at a temperature of 171 degrees centigrade. Within the oven is air at a temperature of 93.4 degrees centigrade and atmospheric pressure. Assuming that natural convection conditions hold near the plate, and that is for this case the average Nusselt number is given as this relation, find the average heat transfer coefficient and the heat taken up by air per second per meter width. Okay. So, the relation for the Nusselt number is given. So, you have to use it, and properties for air. So, it is not water. Okay. Is evaluated at a film temperature 405.2 Kelvin and beta thermal conductivity, kinematic viscosity and Prandtl number are given. So, first you calculate the Grashof number, check whether flow is laminar or turbulent. So, you can see it is G beta Tw minus T infinity into H cube by nu square. So, Grashof number you can write as 9.81 into 2.47 into 10 to the power minus 3. Tw is 171 minus T infinity is 93.4 and H is 0.609, okay, divided by nu square. So, it will be 2.663 into 10 to the power minus 5 square. So, if you evaluate it, you will get Grashof number as 5.985 into 10 to the power 8. So, you can consider the flow is laminar, however, the Nusselt number relation is given. Okay. So, you have to use it. So, using given correlation, okay, you can write Nusselt number as 0.548, Grashof number into Prandtl number to the power 1 by 4. So, from here you can see you can calculate 0.548, Grashof number you have already calculated and Prandtl number is 0.72. So, Nusselt number you will get as 79.07. So, now Nusselt number you can write as average heat transfer coefficient into H by K. So, it will be 79.07. So, average heat transfer coefficient you can calculate as 79.07 into thermal conductivity is 33.2 into 10 to the power minus 3 divided by 0.609. Okay. So, from here if you evaluate this, you will get 4.181 watt per meter square Kelvin. So, average heat transfer coefficient we have calculated. Now, we are asked to calculate the heat transfer rate, okay, per unit width of the plate. So, that you can use the Newton's law of cooling. So, we will write the heat transfer rate per unit width as q prime, that means q by b. Okay. So, per meter actually. So, it will be h bar Tw minus T infinity into h. Okay. So, it is 4.181 into 171 minus 93.4 into 0.609. So, if you evaluate it, you will get 197.57 watt per meter. Okay. So, this is the heat transfer rate. So, now let us discuss about the next problem. For natural convection heat transfer from a horizontal circular cylinder, the following correlation can be used for Rayleigh number in the range of 10 to the power 5 and 10 to the power 12. So, Nusselt number correlation is given for the natural convection heat transfer from a horizontal circular cylinder. So, horizontal circular cylinder you have. Okay. So, from here this is the correlation given. Determine the rate of heat loss per meter length from a 0.1 meter outer diameter. So, outer diameter is given as 0.1 meter, and if this is the length, then your area will be pi d L. Okay. And per unit length it will be pi d. So, determine the rate of heat loss per meter length from a 0.1 meter outer diameter steam pipe placed horizontally in ambient air at 30 degree centigrade. Okay. So, T infinity is 30 degree centigrade. The pipe has an outside wall temperature of 170 degree centigrade. So, Tw is given as 170 degree centigrade, and emissivity also given. Okay. So, you have to find what is the radiative heat transfer rate. Okay. So, again the properties are calculated at the film temperature. So, you can see your film temperature is 373 Kelvin and beta will be 1 by 373. So, you can calculate the beta. And thermal conductivity, kinematic viscosity and Prandtl number are given. So, you can now calculate the Grashof number first. So, Grashof number based on the diameter G beta Tw minus T infinity divided by nu square, okay, into d cube. So, you can see G is 9.81, beta 2.68 into 10 to the power minus 3 into 170 minus 30, and diameter is 0.1. So, to the power cube divided by 23.13 into 10 to the power minus 6 square. So, Grashof number you will get as 6.86 into 10 to the power 6, and Rayleigh number based on diameter will be product of Grashof number into Prandtl number. So, it will be 6.86 into 10 to the power 6 into 0.688, and you will get as 4.72 into 10 to the power 6. Okay. Now, using the given correlation you can calculate the Nusselt number, and from there you can calculate the average heat transfer coefficient. Once you know the average heat transfer coefficient, then you will be able to calculate the heat transfer rate. So, from this relation, okay, you calculate the Nusselt number using the given correlation. Okay. Nusselt number you can calculate as 0.6 plus 0.387, Rayleigh number to the power 1 by 6. So, it will be 4.72 into 10 to the power 6 to the power 1 by 6. Okay. and in the denominator 1 plus 0.559 divided by Prandtl number. So, it is 0.688 to the power 9 by 16 to the power 8 by 27 square. Okay. So, if you evaluate it, you will get as 22.8. Okay. So, now you calculate the heat transfer coefficient. So, Nusselt number is H d by K. This is your average heat transfer coefficient 22.8. So, H bar will be 22.8 into thermal conductivity. So, this is 32.1 into 10 to the power minus 3 divided by diameter. So, it is 0.1. So, you can calculate this as 7.32 watt per meter square Kelvin. Okay. Now, you can calculate the heat transfer rate per unit length, okay, because A is pi dl. So, we will write the per unit length. So, it will be pi d. So, Q prime convection will be just Q by per unit length. Okay. So, it will be H bar, okay, into area. So, area per unit length. So, it will be pi d T w minus T infinity. Okay. So, this will be 7.32 into pi into 0.1 into 170 minus 30. So, you will get 321.95 watt per meter. So, we have calculated the heat transfer rate from the natural convection. Now, you have to calculate the heat transfer rate due to radiation. Okay. So, you can write Q prime radiation as Q rad by L. So, this is your Q convection is equal to your sigma pi d, your view factor F122. So, F122 will be 1 in this case, you know, okay, T w to the power 4 minus T infinity to the power 4. So, this temperature you have to write in Kelvin. Okay. So, sigma is 5.67 into 10 to the power minus 8 into pi into 0.1 into 1, view factor is 1, and 443 to the power 4 minus 303 to the power 4. So, you will get 482.3 watt per meter. So, now you have calculated heat transfer rate due to convection and radiation. So, total heat transfer rate will be just heat transfer due to convection plus heat transfer due to radiation. So, it will be 321.95 plus 482.3. So, you can write as 804.25 watt per meter. So, next let us consider one problem of turbulent flows. Okay. A glass door fire screen used to reduce exfiltration of room air through a chimney has a height of 0.71 meter and a width of 1.02 meter and reaches a temperature of 232 degrees centigrade. If the room temperature is 23 degrees centigrade, estimate the convection heat rate from the fire's place of the room. So, you can see your wall temperature will be 232 degrees centigrade and the ambient temperature is 23 degree centigrade and height of the plate will be 0.71 meter. In this case, width of the plate is given, okay, 1.02 meter. So, you can calculate the area as product of this height into width. So, properties at film temperature you can calculate for the air. So, it is 400.5 Kelvin, this is the film temperature. So, other properties are given here. So, the Rayleigh number you can calculate as Grashof number into Prandtl number. Okay. So, Grashof number is G beta, the temperature difference, into h cube by nu square, and this is your Prandtl number. Okay, Prandtl number is given. So you can calculate Rayleigh number as G as 9.81 into beta 2.5 into 10 to the power minus 3 into 232 minus 23 h 0.71 cube divided by nu square. Okay, 26.4 into 10 to the power minus 6 square into Prandtl number. So Prandtl number is 0.69. So it is 1.813 into 10 to the power 9, and the flow is turbulent. Okay, so you can use Churchill and Chu correlation for these turbulent flows. So Churchill and Chu correlation is given as Nusselt number .825 plus 0.387 Rayleigh number to the power 1 by 6 1 plus 0.492 divided by Prandtl number to the power 9 by 16 to the power 8 by 27 to the power 2. Okay. So you put the values of Rayleigh number and Prandtl number here. So you will get Rayleigh number we have calculated 1.813 into 10 to the power 9. Okay, and Prandtl number is 0.69. So if you put these values and evaluate it, you will get Nusselt number as 147. Okay. So from here now you calculate the average heat transfer coefficient, and from there you will be able to calculate the heat transfer rate. So we can write H bar H by K as 147. So H bar will be 147 into your thermal conductivity is 33.8 into 10 to the power minus 3 divided by 0.71. So you will get as 7 watt per meter square. So your heat transfer rate you can calculate as H bar into area. So in this case area will be H into width. Okay, width of the plate is also given, TW minus T infinity. So H bar is 7, height is 0.71, width is 1.02 meter into the temperature difference 232 minus 23. So if you evaluate it, you will get 1060 watt. So in today's class, first we discuss about the turbulent natural convection flows, and if the Grashof number is greater than 10 to the power 9, then you can say that the flow is turbulent. So critical Grashof number is 10 to the power 9 to determine whether the flow is laminar or turbulent. Then we considered 4 problems. So while solving the problem, first you need to calculate the Grashof number and check whether the flow is laminar or turbulent, and suitably you use the relation for the Nusselt number. And one problem also we have solved using Churchill and Chu correlation for the turbulent flows. You can solve more problems from any textbook. Thank you.